You know, for pretty much all of human history, we've studied the universe with our eyes, by looking at it. But what if we could listen to it? What if we could actually hear the faint, cosmic echoes of black holes colliding, stars exploding, the very fabric of space-time vibrating? Well, today we're diving into the absolutely incredible technology that's making that a reality.
I know, it sounds a little weird, right? But just stick with me on this one. Because it turns out that the same annoying force that makes your socks stick together right out of the dryer is one of the single biggest headaches for scientists trying to listen in on the cosmos. And solving this cosmic static cling problem, well, that's the key to unlocking a whole new era of astronomy.
So what are we even listening for? Well, these aren't your typical sound waves or light waves. They're gravitational waves, literal ripples in space-time itself, sent out across the universe from the most violent events imaginable. But they are incredibly, almost impossibly faint. I mean, think of them as the whisper of a whisper from a billion light years away.
So how in the world do you even begin to catch a signal that faint? The challenge is just immense. It requires some of the most sensitive instruments ever built by humanity, and they have to operate in the perfect quiet of deep space.
Okay, so take a look at this. This right here, this is the heart of the whole operation, an inertial sensor. You can see the diagram and a photo of the real deal. And inside this beautiful gold-plated housing is the key to everything, a perfectly crafted cube called a test mass that's designed to just float there in absolute stillness, waiting for a gravitational wave to nudge it, ever so slightly. This little cube is called the test mass, and its only job, seriously, its entire purpose, is to be the universe's most perfect listener. It's engineered to be completely isolated from everything, vibrations, magnetic fields, the whole shebang, so that the only thing that can possibly move it is that pure distortion of space-time from a passing gravitational wave.
Okay, but here's the catch. This is where that whole static cling thing I mentioned comes roaring back. Because even in the near-perfect vacuum of space, this perfectly still test mass isn't truly left alone. There's a constant, invisible storm raging all around it.
You might think space is empty, right? Well, not really. It's actually buzzing with high-energy particles shooting out from the sun and from distant galaxies. And these cosmic rays are constantly peppering the spacecraft, and just like rubbing a balloon on your hair, they build up an unwanted electric charge on that perfectly still test mass.
And all that built-up charge? It creates these tiny electrical forces, unwanted jitters, that just push and pull on the test mass. As you can see in the diagram, it creates this electrical noise that's literally thousands of times stronger than the gravitational wave signal they're trying to hear. It is like trying to hear a pin drop in the middle of a rock concert.
So that's the big problem, right? How do you get rid of that charge without touching or disturbing the test mass at all? I mean, you can't just go in there with a dust cloth. The solution, though, is absolutely brilliant. It's elegant, and it all comes down to a tiny flash of light.
And you know, this idea, it didn't just appear out of nowhere. It's been evolving for decades. Back in '95, you had missions like Gravity Probe B using these big, clunky mercury lamps. Then, fast forward to 2017, the LISA Pathfinder mission proved, yep, this whole photoelectric effect thing really works in space. And that brings us to today, where for upcoming missions like LISA and Taji, the focus has totally shifted to these tiny, super efficient UV LEDs.
So how does it work? It's pretty amazing, actually. You shine a very specific wavelength of ultraviolet light onto that gold-coated test mass, and that light has just enough energy to gently knock excess electrons right off its surface. Think of it like a non-contact precision cleaning tool, or maybe even a charge-neutralizing ray gun that just zaps the test mass back to a perfectly neutral state. And the whole goal, the end game here, is to reach this perfect state of equilibrium. The UV light creates this balanced flow of electrons between the test mass and its housing, holding its electrical potential as close to zero as humanly possible. That's how you get the silence you need to hear the universe. But that begs the question, what's the best light for the job?
And this is where we really get into the core of the research paper we're looking at today. Scientists knew this process worked, but they were like, can we do better? They wanted to optimize it, to find the absolute perfect, most precise tool for this incredibly delicate task.
So you had the reigning champion, the standard tool of choice, which was a UV LED with a wavelength of 255 nanometers. But then, the scientists behind this paper came in with a challenger. They asked a really simple but powerful question. What if a longer wavelength could get us even closer to zero? Could it make the instrument even quieter?
And wow, the results were, well, they were pretty stunning. Just look at this table.
It shows how close each wavelength got the test mass potential to that perfect zero. The standard 255 nanometer light, it left a charge of over 68 millivolts. Not bad. But then, look at the 275 nanometer LED. It got it all the way down to negative 12 millivolts. I mean, that is so much closer to a perfect zero. A huge, huge win for precision.
But okay, precision isn't the whole story, right? You also need speed. If there's a sudden charge buildup, you need to get rid of it fast. This table shows us that the 275 nanometer light is still super quick. It neutralizes the charge in about 6 seconds. But look what happens when the wavelength gets even longer. The process slows down. A lot. We're talking hundreds of seconds. Way too slow. So this is the big reveal, the key takeaway. That 275 nanometer UV LED, it just hit the sweet spot. It delivered the absolute best precision, getting that test mass potential ridiculously close to zero, while still being fast enough to do its job when it counts. It really is the optimal tool.
All right, so you might be thinking, okay, so they found a slightly better wavelength for a tiny LED. Why is this a big deal? Well, it matters because this one small technical improvement is actually a giant leap for our ability to listen to the universe.
This number right here, this represents the incredible level of quiet they achieved. With that new 275 nanometer LED, the researchers got the charge noise level down this low. I mean, that level of control is almost impossible to wrap your head around, and it directly translates into getting a much, much clearer signal from the cosmos.
So what does this all mean? Why does this really matter? Well, first, it means quieter detectors. Less electrical noise means a clearer signal. It's that simple, and that leads to better science. It makes it easier to spot gravitational waves that are fainter or coming from much farther away, maybe even from the dawn of time itself. It also provides a crucial new tool for amazing upcoming missions like LISA and Taiji. And finally, it gives scientists more options, allowing them to pick the best wavelength for the job depending on what the sun's doing at the time.
You know, the researchers themselves really summed it up perfectly in their conclusion. They said, the 275 nm UV LED is a promising candidate for the continuous charge management and at the same time for regular rapid discharge operation. So what they're saying is, this isn't just a minor improvement. It's a fantastic new tool that does both jobs, the gentle constant cleaning and the fast emergency zapping, better than before.
And really, that brings us to this final, really thrilling thought. What we're doing here is building senses for humanity that we've never had before. Every single time we make our instruments a little bit better, a little bit quieter, we open a brand new window onto the cosmos. So with this incredible new level of precision, what new secrets, what cosmic whispers are out there just waiting for us to finally be able to hear them?